Welcome to the Image Processing Lab Matlab Coding. Image Processing Programs in Matlab Coding Part 3. So, in the Part 1, we have seen the introduction part of the Matlab and basic Matlab commands execution, display of grayscale images, histogram equalization, design of nonlinear filtering. In the Part 2, we have seen determination of edge detection using operators, two-dimensional DFT, DCT, and in this Part 3, we will see remaining programs.
Our next image processing program is filtering in frequency domain. In the MATLAB, to filter the input signal in the frequency domain, first we have to create the DSP.frequency domain FIR filter object and set its properties. First we have to do this. This we have to set first by using this object and then call the object. This is our object. Call the object with arguments. What are the properties you set for this object? Call with those arguments as if it were a function. I'll explain more about that function. Frequency domain filter. This is the function we are using to create the object. So this is creating a frequency domain filter, FIR filter system object that filters each channel of the input signal independently over time in the frequency domain using the overlap save or overlap add methods. Now we will see the code and implementation within the MATLAB. Now I will show you how to filter the image in a frequency domain. We already discussed different types of filters the MATLAB provided to filter the images in frequency domain, and we also discussed how to filter it. First we have to read the object and set all the properties of the frequency domain to the object, and then call that object with that function. So for this MATLAB is provided pre-code for the an example reduce latency through partitioned numerator. So here it is pre-code. I'll explain this later, uh, but why I'm not running this code here and why I'm not showing the output of this code means this code is implemented this code is implemented by using the signal processing toolbox of the MATLAB, which is not available right now with me. That's why the other code for the filtering of the image in a frequency domain I'll show you by using different types of frequencies. First, I have for this to saving the time, I pre-typed the program. Uh, Listen and see carefully. First, I have taken dim as a uh, variable. Within that, I have a calling Lena program, and after that, I have taken sim as a variable. And within this variable, I am doubling the dim, the image stored within the dim. I'm doubling this, and I have taken two dimensions R and C, and I have given for those dimensions the sim image dimensions. Next, I again for those dimensions again I have doubled those one by multiplying with the to individual row and column. Then I want to add some zeros to the rows and columns. So I have taken pim as uh, a variable for the padding. So I have padded by using the function zeros to the rows and to the columns. And for other one also I have done like that only. Next, for the padding repetition for all the rows and columns, here I have initialized the padding variables, and now for all the rows and columns I have to repeat that padding. For that I have run a loop from 1 to r the rows, and j is equal to 1 to columns. So up to rows and up to columns I have taken two ij indexed variables, and I'm assigning the sim into the pin here. Then now applying frequency domain, center the transform. To center the transformation function, you know this, and if you don't know, please see my transformation lecture provided within the Tritva Kiran blogspot.com. This is the transformation function formula I have expanded written here. And after that I have applied the Fourier transformation, the two-dimensional Fourier transformation upon the Kim variable. Next, I have taken many. First, I'm initializing an n variable to apply the filter operation, and a threshold value is also needed for the filter operation. I have taken uh, filter n is equal to 1, threshold value 10 for here. So now I have to apply low pass filters, high pass filters, high boost filters. Within Gaussian low pass filter, Butterworth low pass filter, and for the high pass filters also the methods Gaussian and Butterworth, and for the high boosting filters also the Gaussian method and the Butterworth method. After that, I'm inversing the Fourier transformation inverse film by applying I fast Fourier transformation 2 upon him. Means the filter operation applied one is stored in a him. Now I am repeating that to all the rows and to all the columns by the transform function formula here. And then after applying inverse transform function, I am removing the padding to all the rows and to all the columns by using inverse transform function. Then I'm creating a real part of the matrix with the rim by using the real function, and I'm using unit 8 for the imaginary part. Now, for the to show the output, I have taken subplot, and I'm here displaying the dim with the original image. I'll show the output of original image and the padding image and the transform centering image, Fourier transform image, inverse Fourier transform image, cropped image. All these filtering operations applied in the sections of the code I'll show. So first, I'm enabling the Gaussian low pass filter. So for this Gaussian low pass filter, GLP, Gaussian low pass filter. First, I'll running Gaussian low pass filter running. See here, it is in a still running position. You can find here. If you got the prompt, then program is executed. Still it is running. Sometime it is taking. Gaussian low pass filter. Mm, some more time it is taking. Maybe next one comes faster because this is running first time. See, this is the Gaussian low pass filter. This is the original image. This is the original image. And after padding the zeros to all the columns, this is the padding image. And after applying transform centering, this is the transform centering image. Next we applied Fourier transform. This is the Fourier transform output image. And next we applied inverse Fourier transform. This is the resultant one. And after that we cutting, cropping this image, cropped image, this one. This cropped image you can see here. This is the output. Now I'm commenting this low pass filter, and I'm enabling the code of Butterworth low pass filter. Again I'm running the program. See here it is running. Now see, we got the output fastly compared to previous one. So this is the original image, this is the padded image, this is the transform centered Fourier transform, whatever the frequency domain filter operations we applied upon the image, all those are displayed here. The cropped one, this is the final output. Now I'm commenting that, and I'll show the upon filtering Gaussian high pass filter. Now I'm running. It is running. Yeah, high pass filter. You got the output. Original image, padding, transformation. Now pause the video. Move the video to the previous content output and see how the low pass filter and high pass filter is changed. Observe the output carefully, the filter operations. In a similar way, we can Butterworth high pass filter and high boost filtering of Butterworth Gaussian also you can run. In this program, in this Matlab code, I'll show how to separate the colors within the image, how to display the separated colors of the image. For that I have taken 200 size first within the variable IM size. Next I am taking the RGB into 3 colors, and for the to separate 3 colors of the RGB, the color image is formed with the RGB. I'm using the function jet function, which is the color map array. Within that it is separating and displaying 3 columns for each color of the RGB. So first we are reshaping by using the reshape of this size. We are reshaping and dividing by using the jet function into 3, and then we are showing the output RGB after dividing the parts of the color, and that is the original image. So up to here our original image is created with the 3 colors. Those are color map image, means it is a 3 column, first column RGB, and then we are separating 3 colors. Each color we are separating. So for that we are splitting arm split function we are using to separate splitting the RGB, and then we are showing that splitted RGB colors within the input image by we are displaying here that one, and then we are displaying separately the green one and blue one and R1 colors after splitting this one, and after that these are in gray colors. After that we are our color representation uh, we have to multiply that one with the 8 because we splitted the colors, and we can after splitting within the splitting operation it is in a gray color. So if we multiply with the Matlab 8R, then those will be displayed as a RGB colored images. For that, first we are doing all blank, means padding with the zeros for RGB, and then for the R color only we are concatenating. This is the concatenate function. We are applying the R for the R color all black, and to the green color also all black we are applying, and for the blue also we are applying this. After that within the montage it is displaying within a window three separated RGB, just R color here, just green color here, just blue color here, separately with the size of 1 by 1 3, with the background color white, and with the border size 10. Now I am running this code. Yeah, we got our output. This is the original image. So by the jet function, this is the color map generated, created with the RGB. Now we splitted the color into three separate ones. This representing red channel, red color, green color enabled here, and blue color here, and then we displayed separately in this way: only red, just green, just blue. This is the output. In this way we can display the we can split and show display uh, only colors, particular colors within the images. Now in this example I'll show you conversion between color spaces. Here this is the example converting between RGB to HSV color spaces. In this example it's showing how to adjust the saturation of a color image by converting the image to the HSV color space. Okay, and then displaying the separate HSV color planes. The color planes are HUE, saturation value also we are displaying, and value also we are displaying for the synthetic image. To do this color space, first we have to read the image. RGB image is readed, colored image is readed, and we displaying the readed image, and then convert the color image into HSV image. So the method is RGB to HSV. It is converting our readed colored image into HSV image. And then
now uh, we have to increase the saturation of the image by multiplying uh, S channel by a scale factor. Here we taking the saturation factor, scale factor is equal to 2. So first we are splitting the HSV image by using the method IMSplit into HSV vector, and then we define the saturation factor to 2. Now multiplying the S vector to the saturation factor. Now we got some values, saturation coefficients. Those are displayed with these cat. Now we are processing the HSV image back to the RGB color space and displaying that one. So to that we have the function method HSV to RGB. Now our HSV image is again converted into RGB, then that one is displayed here. Then we are uh, and now we want to look closer to HSV color space. For this, we are inspecting closer inspection of the HSV color space and create some synthetic RGB image. For that, we are taking reshape of these measurements. Within these measurements, we are creating the synthetic RGB image. And now we are again, after creating the synthetic RGB image, again we are converting that into HSV color space. So for that we have RGB to HSV. Again we are converted the synthetic RGB to HSV, and again we are splitting the HSV image into HSV separate vectors. Now we are for the displaying output we used the method montage, and we taken the window border size 10, background as a white, and now I am running this program, and the observe the output which is moving very fastly. You should pause the video from one output to another output and see the difference of each step output. Now I am running the program. See. So this is the final splitted HSV image. Okay. Again I am running original and then this one. Again I am running this original image. It is changing to HSV image and showing and it is showing synthetic RGB color spaces. Now I'll show you discrete wavelet transform of an image uh, upon single level 2D dimensional discrete wavelet transform. So first we have to load the image. To load the image, generally we are using Amrid. You can also use load function, load method, and apply the image SC upon that. Then generate the color map uh, with the color gray, and then obtain the single level 2D discrete wavelet transform of the image using the order 4 simulate and periodic extension. Then the CA value, CH value, CV and CD. These values we discussed uh, from the presentation. See there, remember that, and apply the discrete wavelet transform of the 2D function single level with the X upon the image X with the sim4 mode per. Then display the vertical details coefficients, approximate coefficients. Okay, so uh, image sec CV, this is giving the vertical detail coefficients, and CA is giving the horizontal approximation coefficients. And when I am running this code in the Matlab, see, image is uh, loaded, and then this is the original image I have taken. This is the original image, and it has given error because output is not displayed, because it requires Wavelet toolbox. I have not downloaded the Wavelet toolbox, that's why it is not given the output. Don't worry, I'll show the output from the Matlab help center. And whenever you have a wavelet toolbox also, then this code will give you 100% correct output. Now I'll show you the output. This is the original image. Then this is the vertical detail coefficient output, and this is the approximation coefficients output. So this is the discrete wavelet transform function DWT on 2D image with a single level. Now I'll show you watershed segmentation method. So this watershed segmentation method is to separate touching objects in an image. We already discussed briefly about this. Now I'll show the experiment MATLAB code how to use watershed segmentation. So in the first step, we have to read the image. Here I am reading the image. To complete fastly, I pre-typed the program in the editor. See here. So within the variable RGB, I am reading the image, and then I'm converting that readed image into grayscale image, and that grayscale image I have stored within the variable I. So my original image is in the variable RGB, and the grayscale image of the original image is stored in the I. And then I used show function to show the original image, and within that original image I'm inserting in the output some text with the size at the pixel values these, and image courtesy of Corel font size 7 I have taken, and horizontal alignment I did, and right alignment I did. So with these uh, dimensions, my original image is displayed when I run this program first. And after that, in the step 2, the gradient magnitude we used. So the gradient magnitude, to compute the gradient magnitude, using the function I am gradient, which is the function calculating gradient magnitude, and the gradients at the borders of the objects are high, and mostly the inside objects gradients are low. This is what this I'm gradient will do, and that calculated gradient object is stored in the gmag. Okay, and then I showed that one also with the name gradient magnitude title. So when I run this program, my second output is gradient magnitude. And after that, segmenting the image by using watershed transform. So this watershed transform directly on the gradient magnitude the with means within the previous step. So apply the function watershed direct function upon the gradient magnitude, which I am storing output in L, and then again I'm converting that into color image RGB, and then I'm showing that gradient watershed transform image segment. For that I have given the title watershed transform of gradient magnitude. So with this you will get the third output as a segment of the watershed segmentation. And then uh, mark the foreground objects. We have to mark foreground objects differently from one object to another object. So here we have a various procedures. Here we used opening by reconstruction, closing by reconstruction, clean. These are the morphological techniques we used for mark the foreground objects. So for that we are using the morphological reconstruction function strel and on the disk with the space 20, and then I'm opening and this morphological reconstruction is assigned in the variable SA. Now I'm opening by reconstruction by using the function I am open, and I am showing that one with the title opening. And then opening by reconstruction using imrod and construct functions to compute opening by reconstruction. So imrod uh, I used to compute the opening by reconstruction, and then construct to construct the segment uh, outer objects, outer gradients to highlight them. So which is which I stored in IOBR, and then I'm showing displaying the output with the title opening by reconstruction method. In the similar way, close function is using for morphological closing with the closing by reconstruction. So we open the reconstruction, then after displaying it and processed it by the construct function, I'm closing that one. And after closing that one, closed image also here I'm showing with the title opening closing. And then now we have to reconstruct and complement the image input and outputs of reconstruct. So for that, for complement the image, we use dilate function. With this, we can reconstruct, means we can complement, and then reconstruct the image, and then complement. Using this, you can complement the image. Then show that output by the title opening closing by reconstruction, both in one window. Then for comparing opening and reconstruction of the image, we have to show some standard opening and closing and remove small blemishes without affecting the overall shape of the objects. For that, we have to calculate regional maxima for the opened and closed foreground markers. For that, we have a function I am regional max for the regional maxima to obtain good foreground markers means the foregrounds are marked very good, uh, highlighted nicely. And then after using this, display the output with the title regional maxima of opening closing by reconstruction. And to help interpret the result, superimpose the foreground marker image on the original image. So we used for the superimpose of foreground marker label overlay we are using and showing here the output regional maxima superimposed original image. See, every step is giving different outputs. We have to observe when I run this program after explanation. Then strel we used for some objects are not marked, and those objects also we have to segment properly, and foreground markers of the objects we have to detect and shrink the blobs. So for that we have to using erosion. For that here I'm using the function strel for these values, and then I'm closing my object, and I'm applied emerald upon the object. Next, this procedure tends to leave some stray isolated pixels that must be removed. For that, you can use uh, B where open, which removes all blobs that have fewer than a certain number of pixels. So B where open function is applied and then again overlaid, then displayed the output with the title modified regional maxima superimposed on original image. Then compute background markers. Now in the second next step we are compute the background markers. We need to mark the background now. For that we are cleaned up image, uh, and the dark pixels belonging to the background, uh, we have to clean up them. So you can start with the thresholding operator. Here we are using the thresholding operator. The thresholding operator is the unbinarized operator. So we are using this thresholding unbinarized operator method to clean up the darkened background. The output is stored within the BW, and then the output is displaying with the title thresholded opening closing by reconstruction. So that for this operation to this next operation the background pixels are in black. Okay, but ideally we don't want background markers to too close to the edges of the object, because we are trying to segment them. So we will thin the background by computing the skeleton by influence zones called skis. Okay, skeleton by influence zones called the skis of the foreground of the BW image, which we calculated here by the unbinarized method. So this can be done by computing the watershed transform of the distance transform of BW. And then we are looking for the watershed ridge lines, DL equivalent to 0, the watershed ridge lines as the result of these steps. So we are calculating the distance of the BW, then applying the watershed method. DL is equal to ridge lines and DL is equal to 0. We are doing, then displaying the output with the watershed ridge lines. Okay, then in the next step we are computing the watershed transform of the segmentation function. So the function am impose min, this method can be used to modify an image so that it has a regional minima only, and only in certain desired locations it has only regional minima. So here you can use I'm impose min to modify the gradient magnitudes of the image so that the region minima occurs at foreground and background marker pixels. For that we are using the I'm impose min for the background and foreground pixels, and then finally compute the watershed segmentation by using the method simply watershed upon this. Okay, then our watershed segmentation procedure operation is completed. Now we have to visualize all the results. Up to now, what are the results, what are the outputs, and step by step we have discussed. We have to visualize them. To visualize them, we are taking dilate function for the background showing and for the foreground showing with the multiple of 2 and 3 respectively, and we are applying overlaying label overlay function upon the label which we dilated the foreground and background, then displaying that with the title markers and object boundaries superimposed on original image. Then we are visualizing uh, the label into RGB color with a shuffle W with jet label. Then it is displayed as colored watershed label matrix. Okay, then finally we used the figure for the window, I'm show function for the original image, hold on, and then I'm show whatever here we have labeled all those outputs. We are displaying with the alpha data in the difference of 0.3 difference, all the outputs are coming. Now, with the title colored label superimposed transparently on original image. Now, I'm running this program, and from one output to the other output, you should pause the video and see the output, because all the steps of this program, the outputs are coming fastly. Okay, pause the video, see the output. I'm running this now. It is running. See, this is first output, this is second output, see, and this is third output. Observe this, fourth, fifth, sixth. Okay, and this is seventh one, eighth one. Okay, colored label superimposed transparent and original image. So what are the uh, outputs are stayed from? These are colored watershed labels. All these are colored watershed labels of these colored labels are superimposed transparently on original ones. Okay, these are the differences. In meanwhile outputs, for the meanwhile steps, you have to pause the video and see the output. Okay. So within the part 3 of the image processing lab programs using Matlab, all the programs coding are completed by this part 3, and all the lectures of image processing theory part and lab coding part, and also for the subject business intelligence, all the lecture videos are available in my blog Tritva Jyoti Kiran blogspot.com and in my YouTube channel Tritva Jyoti. All the best.